Okay, so a little bit on announcements and whatnot. I checked last night. My TAs, I think they were grading homework 3.1. I'm not sure if they finished or not, but if they haven't finished, they will probably finish today. So obviously 3.2 is being graded. These solutions are being posted. 3.3 was due today. How was that? Too bad. Hopefully that was pretty straightforward. It was sort of the same problem over and over again. Here's just one scenario and then asking a few different questions. But I do think that homework is incredibly seminal to understanding the concept of moments. Today, I'm going to level with you that today's lecture is computationally pretty easy, but maybe conceptually a little challenging to understand. And so I'm going to take great care to ensure that what we're talking about today is easily understood, because it is a little three-dimensional, and I am going to try and explain why this topic is even important to begin with. We are engineers, and so I want you to understand what we're calculating and more specifically why we're calculating it, okay? So with that, let me get the lecture notes pulled up. So today what we're going to be talking about are moments about an arbitrary axis, okay? Now to level with you, before we get into the topic, I just want to make sure that we're all clear on the fundamentals of what a cross product is. So a cross product is when we take vector A, vector B, and we want to multiply it. And remember, we have two ways of multiplying vectors. We have a vector A multiplied by vector B yields another vector, which is what we've been doing this whole time. But then we also have where we can take vector A, vector B, multiply them, and get a scalar. Okay, and so that's what we're going to be dealing with a little bit today, is that scalar product, or more specifically, the dot product. Okay, and now I also want to dig a little bit more into the formal definition of the moment, and just make sure that we're all clear on what moments mean when we express a moment in IJK notation. But remember, so the formal definition of a moment states that if we have some point, we'll say a point naught out in space, and we have a force being applied out in space and it's not going through that point, then the moment generated about that point by that force F is computed by the cross product of R and F. So R being the position vector that starts at point naught and points to anywhere along the line of action of F, and then F is obviously your force vector. Now, to be clear, if the force happens to go through the point in question, then your position vector would be 0 and the cross product would be 0. In other words, if a force is going through a point in question, it does not rotate that point. It's just wanting to translate it. Okay, but I want to make sure, again, that we're clear about the definition. So I'm going to go back to an example that we had done a few lectures ago. And I'd referenced this last time, and I'm going to reference it again. So this was the first real moment example that we did, where we had taken our point coordinates, defined our position vectors, defined our force vectors, and then went into the land of cross products. And we got this. Okay, now I again want to recap what this means. Okay, so we have a vector in IJK notation, and we have these terms, negative 7,680i, 28,000 some j, and 28,000 some k. Let's think about what those numbers are. Okay, now remember, we do have the right-hand rule and whatnot, but I want to, again, make sure that it's clear what they represent. So, for example, this negative 7,680 represents a scalar quantity. Negative 7,680 is a scalar. Okay, but what is that? Well, that is the tendency that this moment wants to cause rotation about the x-axis. So this vector represents a moment. This is how much we want to rotate about the x-axis. This is how much we want to rotate about the y-axis. This is how much we want to rotate about the z-axis. So if I want to know how much I want to rotate about a given axis, the answer is ultimately some scalar, right? This is how much we want to rotate about the x, about the y, and about the z. So that expressing the vector in IJK notation gives those tendencies of rotation about our cardinal coordinates, the x-axis, the y-axis, and the z-axis. But my question today is, what if I'm not interested in rotation about the x-axis, the y-axis, or the z-axis? What if I'm interested in rotation about some arbitrary axis, about some random line out in space? So instead of rotating about x, y, and z, so for example, let's say I've got a coordinate system here. So this is the x-axis, this is the y-axis, and this is the z. Instead of expressing rotation about each of these three cardinal axes, what if I want rotation about this axis, the axis from that point just out here? That's going to be the topic of discussion today, is determining moments about an arbitrary axis. Now, before we start diving into this, the first thing I want to express is why. Who cares, right? Why would you care about moments about some arbitrary axis in space? Because that sounds like, it's like, come on, Dr. Mike, that's some weird stuff to be talking about. I'm going to give you a very real reason why this is important. And the real reason is torsion, okay? So in the land of mechanical design, and this is true in civil engineering structures, mechanical engineering structures, what have you, you're going to learn this when you take Engineering 216 next semester or BME 302 for you biomechanical engineers, or biomedical engineers, not biomechanical. Is that when we start delving into the land of stress analysis, what we're going to be doing is we're going to be looking at how elements respond to different types of loading conditions. So how an element responds if we take it and stretch it, right? So it's going to develop some stresses and some strains and ultimate deformations. But what about if we bend it? What about if we shear it? And what we're going to find is that one of the fourth areas is what about if we take an element and twist it, okay? Now, if you have long, slender elements, especially ones that have open cross sections, what I'll tell you is that they behave the weakest when they're being twisted, okay? And so if you have, a good example might be, I don't know, let's say you've got a transmission tower. So you've ever been driving on the interstate, you see those big towers, those big 3D trusses that support the power lines, power transmission lines, you know what I'm talking about? Okay, imagine if one of those towers gets hit with some wind in some weird direction. Some of those elements inside that structure might want to twist, okay? So you've got some random axis out in space and you've got a load going like this. I want to know how much moment is about that axis, because that's how much that element is wanting to twist, okay? So again, I want you to know that I'm not going through this concept just because it's weird and I'm just trying to make things complicated. There are real aspects to why we're talking about this, okay? Does that make sense? Okay, but to go into the math of it a little bit, I want to talk a little bit about the dot product. And that should be sort of a natural extension to what we're talking about here, because remember, the dot product is sort of shorthand for the scalar product. If I take vector A and vector B and dot them, I will get a scalar. And if we're talking about moments about an arbitrary axis, well, moments about the x-axis are represented by a scalar. Moments about the y-axis are represented by a scalar. So ultimately, we should probably be looking at dot products since they yield scalars. Now, we've already had experience with dealing with moments about a given axis, because that's what we did in the last lecture. In the last lecture, we looked at, well, what about moments in two dimensions? What if your forces in the x-axis, what if your forces and your point in question all lie on the same plane? For example, the xy plane. If you have a force on the xy plane and a point on the xy plane, it causes rotation about the z-axis. So when we were dealing with moments in two dimensions, we sort of dispensed with the vector notation, because all we really cared about was that scalar multiple, or that scalar coefficient, okay? So what we need to do is we need to talk about the dot product, okay? Now, like before, when we defined the cross product, we need to define the dot product and specifically what our goals for the dot product are going to be. So let's consider two vectors, P and Q, and let's dot them, okay? Now, I want to define the dot product in such a way that regardless of which vectors I multiply, I get a single predictable answer, okay? So P dotted Q, well, I think one way of dealing with it is I could say, well, P dot Q equals the magnitude of P times the magnitude of Q, because that should work out pretty well. But I can also probably define that a little bit more expeditiously. If you remember, the cross product was defined with the sine of the angle being integrated into the magnitude. Well, we'll define the cross product such that the cosine of that angle is directly integrated between the two. So just like pop quiz, if I gave you two vectors and I said compute the angle between them, you have two ways of doing it. You could use the dot product or you could use the cross product. I personally like to use the dot product because it's a lot easier, okay? How many of you have ever done dots and cross products before? Dot products are a lot easier to do, right? They're a lot less work. So, and we're going to see why here in a second. If you've never seen a dot product before, you'll kind of get the gist of it. Now, like last time, we were able to derive how a cross product is computed by looking at our three essential vectors, looking at I, J, K. We're going to do the same thing here with the dot product. If we understand the result of the dot product, and we can get the of the I, J, K vectors, then we can get the result of the dot product of any vector. Okay, so I've got I, J, and K. So let's think about the formula here. So we want the dot product to be the magnitude of vector 1 times the magnitude of vector 2 times the cosine of the angle. So what does that mean? Well, each of these vectors has a magnitude of 1, right? The I vector is 1 unit long. J vector is 1 unit long. Same thing with the K vector. Now we're dealing with cosines. We're not dealing with sines. So what is the cosine of 90 degrees? It is 0. What is the sine or the cosine of 0 degrees? It is 1. Okay, so let's see what happens when we take vectors and dot them. What about taking a vector and dotting it with itself? What about I dot I or J dot J? Well, what about I dot I? Well, I dot I is going to be the magnitude of I times the magnitude of I times the cosine of, in this case, 0 degrees, because the angle between I and I is, well, it's 0. There's no angle between them, right? So we have 1 times 1 times 1, right? So if I take I and I dot it with itself, I get 1. If I take J and dot it with itself, K and dot it with itself, I get 1. So anytime you take one of the unit vectors and dot it with itself, you get 1. What if you take opposing vectors? What if you take I dotted with J or I dotted with K or anything like that? Well, the magnitudes of those vectors are all 1, but each of these vectors forms a 90-degree angle with its other counterparts, and the cosine of 90 degrees is 0, right? So that's why any of these vectors dotted with their opponents, if you will, is 0, right? So what I can do is I can take the same thing I did last time, and I can remember last time how I went and carried each one of these through and chucked it all out. Well, I can do the same thing, but the formula gets a lot simpler with dot products, right? Because what you find is that if you extend all this out, anything where an I is dotted with itself or a J is dotted with itself, etc., is 1. All the other opposing terms are 0. And so you get a very nice plug and chug formula for the dot product. And for those of you that have done a dot product, this is how you do it, right? Pretty simple, right? I don't know if you all who have done dot products before, was it explained to you this way? I'm just curious. So was it explained that way? So hopefully, does that make sense? So, okay, so I wanted a systematic way of doing it. And I'm not sure if when you were doing dot products and cross products, if it was ever explained that way as to how you actually compute the dot product and the cross product, but hopefully that gives you a little bit more insight into how to do it. So any questions on that, or why to do it, I guess you could say. I'm good? Okay, so what are the applications of the dot product? Okay, so like why? Again, it's like, who cares? Like, it's great. You can dot 2 vectors. Why would we care? Okay. Well, there are some 3 real important, what I would call geometric applications of the dot product. And when I say applications, I'm talking about applications related to geometry. Okay. So the first is, again, computing the angle between 2 vectors. Like I said, I think that the dot product is more, it's easier to do that calculation. We can compute the volume of what's called a parallelepiped, and you never get to say that word very often. You know, I think I only say that word about once a year when I teach this class. So that's it. That's my one. Parallelepiped. There, I said it again. So got to live a little. Okay. So if you have a 3-dimensional prism, if you will, you can write vectors to describe the 3 edges. And then you can take what we call a mixed product to determine that volume. So you cross 2 of the vectors, and then you dot it, the result of that, with the 3rd one. Okay? But the 3rd application is what I'm calling the projection of a vector on an axis. Okay? And that's really what's important to us. Okay? So if I have some vector out in space, so this vector P, and let's think about this in terms of moments. Okay? So let's say this vector represents a moment out in space. So some amount of moment about the x-axis, some amount of moment about the y, some amount of moment about the z. What I can do is I can determine the amount of moment generated about an arbitrary axis, let's say some element in some system that I'm concerned about twisting. What I can do is I can take that vector and I can dot it with the unit vector describing this axis. And that will tell me how much moment is generated about an arbitrary axis. Okay? And where we get that, if you're wondering, like, how does that work? It's honestly just a little bit of trick. So if you have some arbitrary axis out in space and you want to project that onto some line, well, that magnitude is just this vector times the cosine of that angle. And by now you know that the dot product is very intrinsically linked to the cosine of the angle formed between those two vectors. So basically all you're doing is just dotting this vector with a unit vector for the axis in question. There you go. So if I want to compute moments about an arbitrary axis, what I do is, the first thing I do is I can compute the moment, r cross f, right? And then I can dot that moment with a unit vector about the axis in question, okay? Now, you could also set it up in a big 3x3 determinant and handle it this way. You could just do the calculation all at once. That's fine too. But hopefully you see that this is a pretty straightforward application. Does this concept kind of make sense? Everybody okay with this? Don't worry, we're going to have an example going through it. Okay. All right. So let's look at this example. And so this is kind of an idea of what I'm talking about when I say trying to determine the amount of twisting. So I have here this frame, okay? This frame is hinged at, this point and this point, and it's being supported by a couple of cables, okay? Now, the tension in this cable, in both of these cables, because it's the same rope, is 450 newtons. So I want to determine how much tension this cable, this tension or this moment is generating about this line. How much is this tension wanting to twist this line? Okay, that's what I want to try and determine. Because maybe what I'm trying to do is design some element to withstand that amount of twisting in that region. Okay, so you're going to find that while the geometry might be a little hard to wrap your head around right now, it's actually pretty straightforward. Let me go to the notebook because I've already got all this right here, and we'll get into it. Again, I know this concept is probably a little spacey right now, but I think you're going to find that it's ultimately a pretty systematic problem. So let me make this a little bigger, and we'll get into it. I'll give you all a sec to copy some of this down, and then we will jump right into it. And for those of you that came in a little late, I brought back the results of your celebrations. After class, we'll have a little bit of time. They're organized alphabetically, so you can just grab them whenever you're done. Again, they're not marked because that's worth the exam report that each of you got an individual email for. So yeah. Okay. All right. Now I'm going to do a little bit of sketching right here. Okay. So let's read through the problem again. Let's just make sure we understand what's going on. So the frame is hinged at A and D. It's supported by a single cable that passes through a ring at B and is attached to hooks G and H. So knowing that the tension in the cable is 450 newtons, determine the moment about the diagonal AD of the force exerted on the frame by the portion BH of the cable. Okay. So what this means is that for this problem in question, okay, what this means is that this is our axis, right? So our axis, so we're doing a moment about an axis example. The axis is AD, okay? So what we're ultimately going to need is a lambda vector about that axis, okay? We're going to need a lambda vector about that axis. Okay. Now, we're determining the moment about that axis generated by a certain force. And that force is by portion BH of the cable. So the force for this problem is this. This is the force. And so maybe we'll call that force tension BH. So in order to do this, we're going to need 3 vectors. We're going to need a lambda vector, a force vector, and we're going to need a position vector. Now the thing about moments about an arbitrary axis problems is that if you thought you had a lot of options for R before, you definitely have a lot of options for R now. Because R needs to start at the axis in question, and it needs to point anywhere along the axis or the line of action of the force. So we can have a vector, an R vector that goes from here to here, from here to here, from here to here, here to here, here to here. As long as it starts at the axis in question and it ends on the force, the line of action of the force, you're going to get the same answer. So it's pretty nifty. All right. So with me so far? Okay. Now again, I think with all 3-dimensional problems, I genuinely think that the hardest part are the point coordinates. All right. So for this problem, we're really only going to need 4 of them. So we're going to need point coordinate A, B, D, and H. All right. And actually, let me do this. Let me go ahead and say that these are all in meters. So let's see if we can write this out. So I'll do the first one. So point A is right here. So it doesn't go anywhere along the X. It doesn't go anywhere along the Y. And as for the Z-axis, it's going out this way, and it's going out this much right here. So that's going to be 0, 0, 0.75. Does that make sense? All right. So how about point B? Somebody get me a coordinate for that. What's the X coordinate? 0.5. The Y coordinate? Yep. And the Z coordinate? All right. Now the D coordinate, what's X going to be? One. Y? Zero. And there you go. Again, I honestly think this is the hardest part. This part right here. Okay? If you can handle this, I think you're going to find the rest is very mechanical, very rote, very plug and chug. All right, last one, H. What is X coordinate? 0.875. What about Y? 0.75. What about Z? 0. It's exactly right. I want to stop for a sec before we move on. I think that's the most difficult part, okay? Does anybody have any questions about that? Any values that didn't make any sense or you didn't know where they came from? And again, if you do, don't hesitate. Again, you're all paying cash money to be here. I want you to get your money's worth, as it were. Sound good? Yes?
Where did the 1 come from on D?
The 1 come from on B or D?
D.
D. Oh, okay. So, all right. So along the x-axis, so we're going this way. So we're going a half and then another half. No, that's fine. Don't hesitate if you got questions like that. I want you to ask him. You ask that question, I guarantee there's probably somebody else in here who's thinking the same thing. So, anybody else? This is good stuff. All right, good. Okay. All right. So in order to compute a moment about an arbitrary axis, okay, so in order to do this calculation, so moment about AD, okay, what we're going to need to do is determine three vectors. We're going to need to determine a lambda vector dotted with R cross F, or in this case, the tension about BH, right? That's our goal. That's what we got to do. Okay, so we're determining the moment about this arbitrary axis, and in order to determine the moment about axis AD, we take the actual moment R cross F and we dot it with a vector defining the axis in question. So we've got three vectors that we need to define. So we'll take each of these vectors one at a time, define them, and then go through the math. So let's just start in order. Let's start with vector AD, okay? So let's start, losing my string here, with the unit vector lambda along the axis AD. Okay? I think by now we've got enough experience doing stuff like this, but just to make sure that we're all on the same page, so the first thing that we need to do is we need to define vector AD. Okay? Now, in order to do that, what I'm going to do is I'm going to take the coordinates of D and subtract them from the coordinates of A. So I'm going to do it in reverse order. Okay? So I'm getting 1 minus 0 is 1, 0 minus 0 is 0, and 0 minus 0.75 is negative 0.75. Okay? And to be clear, I think that represents what's going on in the real problem, right? So I think I can point this out over here on the screen. So if I go from A to D, I'm going in the I'm going in the positive x direction 1. I'm not changing on the y, but for the z, I'm going back. I'm going back negative 0.75. So see how our math matches what's really going on in the problem? Everybody okay with that? All right. So therefore, scroll this down here a little bit. So therefore, AD, you could write this however you want, but I'm just going to say it's I minus 0.75 K. And what I'll do is I'll say in meters. So if I have a vector, how do I take that vector and determine a unit vector? How do I do that? Divide it by its own magnitude. So we need the magnitude of this vector. That D looks like a P to me. So if I break out the Casio FX 115 ES Plus or similar scientific calculator, what is the magnitude of that vector going to be? Say it again. Thought I heard somebody say it. 1.25, is that right? Do I have a second? All right. So therefore, lambda AD is 1 meter over 1.25 meters times I plus, we can go ahead and say minus at this point. I think that'll be simpler. Minus 0.75 meters over 1.25 meters times K. And so therefore, lambda AD is 1 over 1.25, I believe that's 0.8, right? Times I minus 0.6 times K. And what are the units for that? There are none. That's unitless. So there's one of our vectors. So far, this really shouldn't be anything that's drastically new. It's the same stuff we've been doing this whole time. Okay? Sound good? Now, I am going to I'm going to change my order of calculations a little bit, and I'm going to do the force vector next. And the reason I'm doing the force vector next is because we should be familiar with doing that one as well. So the force vector which is along line BH. So how do we define a force in 3 dimensions? Now, we've done this before. So we need a vector for BH. We divide that vector by its own magnitude to get a unit vector, but then we multiply that vector by the magnitude of the force, right? To get a force vector in 3D. We've done that before, right? And so what was the magnitude of that force again? It was 450, is that right? Okay, so let's handle that. So let's say note magnitude of the vector is, oh, I'm skipping stuff. Is 450 newtons. All right, so BH is what we got to get first. And so we're going to do it the same way we just did. We take the coordinates of point H, which was 0.875, 0.75, and then 0, and then vector B, which is 0.5, 0, 0.75, and we're going to subtract those. All right? And so let's see if my mental math's working out pretty well this morning. I've learned to make sure that I have coffee before I do significant calculations. So 0.875 minus 0.5, that's 0.375. 0.75 minus 0 is 0.75. And then that's negative 0.75. So therefore, BH is 0.375 I plus 0.75 J minus 0.75 K. And that is in meters. So, same process as we've done before to define a force. Okay? So, we determine the magnitude of that vector using our old friend the Pythagorean theorem. And so what do we get for that? Anybody got that one for me? 1.125. Second? All right, cool. All right, so now we determine the unit vector. Okay, so what are we going to get for this first term? So like whatever we get for this first term, these two are double that. So it actually comes out to a nice even fraction, or somewhat even fraction. 1/3. So this is 1/3, this is 2/3, and that's 2/3. So therefore, we could write this as 1/3 I plus 2/3 J minus 2/3 K. Is everybody okay with that? That's our unit vector. Now we need to multiply that by the magnitude. So therefore, the force vector is the magnitude times the unit vector. So 450 newtons times 1/3 of I plus 2/3 of J minus 2/3 of K. So what we get, I think I can do this one in my head. So 450 times 1/3 is 150. Then the rest are 300. So 150 I plus 300 J minus 300 K. And that is in newtons. I'll tell you, one of the things you find about statics is that, I mean, this lesson is about moments about an arbitrary axis, and we haven't even got to that yet. It takes a while just to go through and define the forces. That's just sort of the nature of the beast. So, but ultimately, this stuff that we've been doing so far shouldn't be all that challenging because we've been doing this, for the past few lectures. So, the new stuff is what's coming here with the position vector. But so far, everybody good? Okay, so let's talk about this position vector. Okay, now this is a really wild problem because there's multiple different position vectors that we could get, and we would all get the same answer. So I'm going to try one that's maybe a little more challenging, and let's see what happens if it gets a little simpler. So position vector. Okay, so let's recall the definition, all right? So it needs to start anywhere along the axis in question. So in this case, we're talking about AD. And it needs to end anywhere along the line of action of, getting ahead of myself, of F. Now, in this case, the problem, the F is BH. So really, any permutation from the axis to the line will give us the same moment at the end of the day. So what I'm going to do is I'm going to try R. Let's just try one. Let's just say from D to H, right? So we could go, so just so you see the pattern, we're going from D to H. We could go from D to B. We could go from A to B. We could go from A to H. We could use any permutation and we would get the same answer. But let's just try D to H. Let's just see what happens. All right, so H is 0.875, 0.75, and then 0. D is 1, 0, 0. So we get negative 0.125, 0.75, and 0. So therefore, R, and we did that from, or to H from D, is this. But that's not the only one. We could have oodles and oodles of different position vectors, and we would get the same answer. And I'm going to show you something here in a second, maybe something to try at home. Okay? See how we're doing on time. We're doing great. All right. So now we're finally getting to what I would call the real new stuff. The new stuff now is computing this moment. Now, the way that we compute this moment is we take lambda and we dot it with R, in this case RHD, cross with the tension. Now, let me show you how you set this up, okay, because it's really easy. Now, normally when you're setting up a cross product, you put the R terms here, put the F terms here, and then what you would put up here is I, J, and K, right? So this right here, this is the R vector, this is the F vector, so maybe I'll write that out. Maybe I'll say this is the R vector, this is the tension vector. And normally you'd put like I, J, K, but we're not going to do that. Because we're ultimately wanting a scalar at the end of the day, what we're going to put is this. And that is just the lambda coefficients. And then what we can do is we can run our cross product out the same way that we had done it before, only instead of writing I, J, and K, we write 0.8, 0, and negative 0.6, and then just chug it out. So let me show you how that works. So if we were doing the I term, we'd have a 2 by 2 that looks like this. Right? So we would cross out this row and column and get these 4, and then we would have an I here, right? But instead of I, we're going to write 0.8. Then we subtract our J term. This one's going to be pretty easy, right? Because our J term is going to be 0. Actually, I know I'm going to run out of room, so let me move this over. I got to say that's one of the things that you can't do on a whiteboard. I'm a little spoiled with that. Then plus our K term is negative 0.6. So what are we going to get? So we're going to get 0.8 times what? Okay. So this times this minus this times this, that's 0. So 0.75 times 300, what is that, 225? I think that's right. So negative 225 minus, and this whole thing right here is going to be 0, right? It doesn't matter because whatever the determinant is, that's 0. So that's 0 plus negative 0.6 times, and then what do we have here? So we got 0.125 times 300. Get a plus. 37.5. I get that right? I do. You tell me. Everybody's looking at me like I didn't bring my Casio FX 115 ES Plus or similar scientific calculator. Okay. All right. So somebody tell me what you get at the end of this. I'm going to do some work this morning. Come on. So that times that plus that times that. I think I can eyeball this and tell you it'll be negative. What's that? Did I make a mistake?
Yeah, it should be 0.75 instead of 0 and positive 300 instead of...
You're, hold on, let's see. You're right. That's right. Whoops. This one needs to be... That's correct, right? Okay, so if that's right, that means this is wrong. Whoops. I hit the eraser. So what goes in here? Yep, that's what I got. So seconded. Thank you. All right, so what do we get at the end here now? So this is going to be positive. This is going to be negative, but I think it's going to be negative at the end just based on the magnitudes. Do I have an answer for me? 90. Do we have a second? All right. I got 90 at the end, so I must have, but I didn't do the intermediate steps. So therefore, the moment about that axis is negative 90, and in this case, it's Newton meters. We don't use the term joules when it comes to moments. We just write it out as Newton meters. So that's the answer. Now, I know that we're all are itching to leave, but I want to say something before we leave. Okay? I'm going to say note what you should do on your own. Other R vectors work. Vectors. In other words, try RBA, and this one is only 0.5I. So if you replace that middle row with just 0.5, you will get the same answer. Got to try it out and see. All right, I'm going to pull the QR code up again. If you did not grab your exam, please come grab it. That's all I got. I will see you all on Friday.